Today we're going to be switching gears away from set theory and back to the world of numbers. Talking specifically about percents. Chapter 8 is really dealing with a lot of financial stuff, and percents is kind of our first step into that. So we've got to discuss some things about percents themselves, and namely how they relate to numbers that we're already familiar with, things like fractions, decimals, how we can switch between representing a number as a fraction and as a percent, and so on. We are going to take a look at how we can apply percents to real-world problems, calculating things like sales tax, hence why I'm asking what kinds of things we should shop for today. And then we'll talk about percent change. So first and foremost here, what is actually a percent? I think if we break down this word, it really gives us a good sense of what a percent actually is. Because this word cent, if you think like there are 100 cents in a dollar, or there are 100 years in a century, this root cent really does mean 100, so we can quite literally translate per cent to per 100. And so we can think about a percentage almost like a fraction. In other words, we could say something like 65% is really 65 parts per 100. In other words, it is quite literally 65 100ths of a whole. Right, and by that definition, it makes it pretty nice for us to convert percents to fractions. So for example, we could express 35% as a fraction because 35% literally means 35 per 100, or 35 100ths. Now, of course, we can simplify this, and we should, right? Each of these has a factor of 5. 35 is 5 times 7. 100 is 5 times 20. And so when we reduce that by canceling out the 5s, we're left with 7 20ths. But the idea of parts per 100 still holds, and it still allows us to convert between percents and fractions. And for the most part, that's all there is to it. I could give you one example where this gets just slightly trickier than that. Say we wanted to express 3.1% as a fraction. We can still sort of think of this as 3.1 per 100, or 3.1 over 100, but 3.1 over 100 is not really a fraction, so we can't stop here. Right? A fraction needs to be an integer over an integer. And so we actually need to scale this. So if we begin with 3.1 over 100, we've got to scale that in order to get an integer in both cases. Now, 3.1 only having one decimal place, in order to get that to be an integer, we can multiply by 10. And so we'll multiply the top and bottom by 10 to scale this to 31 over 1,000. Now I'll slow down just a little bit here to point out a few things, because we are taking, or we are relying pretty heavily in all of this through a lot of stuff that we've done previously, right? So some quick refreshers here. Number one, this guy here, we can multiply anything by 1 in terms of x over x to quote-unquote scale that fraction. We change the denominator, we change the numerator, we change what it looks like, but fundamentally the number is still the same. We are going from 3.1 to 31 by multiplying by 10. Right? We talked about multiplying by powers of 10 a lot when we talked about scientific notation. Multiplying by 10 is equivalent to moving the decimal place, moving the decimal point right. Right, we moved it from 3.1 to 31. And lastly, we know that this here, 31 over 1,000, is fully reduced because 31 is prime. And so there's a lot of stuff going on here, right? This one, number 1, is probably coming from like 5.3 or 4. This one in number 2 is probably coming from 5.4 maybe, I forget exactly. And then number 3 here, we're going all the way back to 5.1. So we're really taking a lot in this chapter from the stuff that we've already done in chapter 5. So hopefully we're feeling confident about those things. If not, it's definitely worth going back and getting a refresher on some of this earlier stuff from chapter 5. Also remember, just as a reminder as we go, if you do have any questions at any point, just type them in the chat, and I'm periodically checking back and forth between the whiteboard and the chat. And that's how we can take a percent and make it a fraction, right? Because the idea of percent really means per 100. But how about if we wanted to go in reverse? If we wanted to take a fraction and express it as a percent. This depends a little bit on the specifics of the example, but in some cases, at least in the same way that we did the scaling here, by scaling this fraction to make it in terms of 1,000, we can do that with something like 7/4 as well. So express 7/4 as a fraction. Right, and the reason that we can do that is because 100, to express this as a percent, we need it as per 100, and 100 is a multiple of 4. So we're going to be able to scale this easily by multiplying it by something. So in the cases, I'll say in the cases, or if 100 is a multiple of the denominator, we can scale the fraction. In other words, we can take 7/4 and multiply it by 25/25, because 4 times 25 is equal to 100. And this will give us something per 100, something as a percent. Now, 7 times 25, if you do the quick math, is 175. And so that tells us we have 175 parts per 100. So this is 175 per 100, or per 100 literally meaning percent. This is 175%. Ah, yes, Morgan, that is true. Express 7/4 as a percent. Let me fix that. There we go. Express 7/4 as a percent. Okay. Now, this works really well when we do have a denominator that has a multiple of 100. But in the case where we don't, say we had something like 5/8, and so we wanted to express 5/8 as a percent. Here we can make this a decimal first and then translate the decimal to be a percent. So what we'll do here is, I'll say if not, as in if 8 does not have 100 as a multiple, which it doesn't, we can divide to get a decimal. Now, here's another instance where we're going to have to think back to Chapter 5 when we talked about translating from fractions to decimals, or think back to the math you did growing up when we did a little bit of long division. Here we're dividing 8 from 5. And so we've got to use long division. 8 does not go into 5 anytime, so we've got to put our decimal place and add another digit. 8 does go into 50 6 times. 6 times 8 gives us 48. We do our subtraction. 50 minus 48 is 2. 8 does not go into 2, and so we add another digit. 8 does divide 20, 2 times specifically. 2 times 8 gives us 16. 20 minus 16 gives us 4. 8 does not go into 4, but when we add another digit, 8 does go into 40 5 times. And then, of course, 5 times 8 gives us 40. When we subtract, we get 0, and we know that we have it. So the fraction 5/8 is equal to the decimal 0.625. Again, I went through that kind of quickly, but if that is something that you are a little bit unsure about, definitely worth going back and reviewing some of the stuff we did in Chapter 5, or just refreshing up on your long division in general. But now what this comes down to is, how do we take a decimal like 0.625 and turn that into a percent? And so we'll come back to this one in a moment, but now we've got to talk how to take a decimal and turn it into a percent. And the nice thing about being out of 100 is that 100 is a multiple of 10. And we have a base 10 number system. In other words, we have 10 digits. So we have a ones place and a tens place and a hundreds place. And likewise, we have a tenths place and a hundredths place. So what that means is that it actually, to express something in a percent, works really well. It's highly compatible with the number system that we already use. And because of that, all we really have to do here is multiply by 100. Or in other words, slide the decimal 2 places to the right. So for instance, we might want to say express 0.013 as a percent. Well, this is the same as 0.013 times 100, or we are sliding that decimal place over by 2 places, which would give us 1.3, or more specifically, 1.3%. This would be the same idea if we had to express something like 4.81 as a percent. We still want to multiply this by 100, 4.81 times 100. Or equivalently, we're thinking about this as sliding our decimal place over 2 points to the right. And so 4.81 would be 481%. And so let's return to our previous question. Express 5/8 as a percent. We have 0.625. And so if we have 0.625, we need to multiply that by 100. Or, again, in other words, slide our decimal place over by 2. And so that would give us 62.5%. Morgan is asking, wouldn't you add a 0 in front of the decimal place? You're talking about here, I'm assuming. In some sense, yeah. It's sort of like if you're writing numbers out formally, you definitely always want to put that. If you're just kind of taking it as a quick note, as we're doing here, like it's more of like the reason I'm not putting it is more about just kind of speed rather than accuracy, right? We know when we're writing this, because we're also talking about it, that we mean 0.625. And we also know that what we're going to do with that is just multiply it by 100, and so that 0 that would have been out front is sort of irrelevant in the end anyways. And so because of that, yeah, I'm sort of taking the lazy step of not writing a 0 here or not writing a 0 here. And you would want to make sure for sure that you do that if you were ever like writing these numbers and trying to communicate something clearly in writing. But because of the nature of what we're doing here, and then I'm kind of describing it as I go as well, and just being quick with the notation to get us to this place, I'm leaving that off. But it does fundamentally mean the same number. All right. Good questions so far. So this leaves us with one more combination here. We also want to be able to take a decimal. Nope, I did that one already. We also want to take a percent and make it a decimal. And so you might imagine that if going from a decimal to percent means multiplying by 100 or sliding 2 decimal places to the right, going in reverse will mean that we have to divide by 100 or slide our decimal 2 places left. So for instance, we might want to express 19% as a decimal. When we write 19%, we assume that our decimal is here, and so to slide that over or divide this by 100, that's going to give us 0.19. And you'll notice I'll put it here, the 0.19, because I'm not just using this as a quick intermediary step. I'm actually communicating this as my final answer. So to say 0.19 is going to be more important now than it was to just kind of quickly note through 0.625 on the last one. Similarly, I could ask to express 106% as a decimal. And our same idea will still apply. We've got 106, our decimal starts here. We're going to divide that by 100, which is sliding our decimal place over 2 to the left, which would give us 1.06. Now you should notice here that these two answers look a little bit different because percents being out of 100 would revolve around 100 100ths, which is specifically 1. In other words, what I'm trying to say in a really complicated way is 100% is equal to 1. So anything that is greater than 100%, right? So a percentage that is greater than 100% also has to be greater than 1. A percentage that is less than 100% also has to be less than 1, like we see up here. Right, so 106%, this is greater than 1. 19%, this is less than 1. That's an important thing to keep in mind. All right, great. So we can work with percentages a little bit, and that's fantastic, but who cares? Why do we need to know about percentages? Well, percentages come up quite a bit in everyday life. In fact, every time that you buy something, or at least most of the time that you buy something, percentages factor in to your life. Specifically in terms of a sales tax. Right, when you go to Amazon and you decide to purchase something, or you go to your grocery store and you decide to purchase something, or you go to wherever you can buy items and goods and purchase something, there is a sales tax that goes along with that. Usually it's a percentage that is determined by local governments. But basically, the government takes a percentage of the money that you pay on that sale as a tax. And so the sales tax, the money that you actually end up paying to the government and not whoever it is you're buying your goods from, is going to be the tax rate, which is always given as a percentage, but needs to be multiplied as a decimal, times the actual item cost. Right, so you have to take 6% of the item cost or 8% of the item cost, and that's how much money you have to pay on top of the cost of the item that you're purchasing that gets given to the government. And so let's do a little shopping. Let's suppose though, and I don't know exactly what the sales tax is on things in Rhode Island, or if it even applies if we buy things online, or how exactly it applies online. But let's suppose that the tax rate is 7.5%. Okay. And now the rest of this we're going to be computing on the fly, because I don't know what you guys suggested we should buy, so I'm going to take a look now. Let's see. We've got some good suggestions here. I'm going to write these down as we go so you guys can see. We've got coffee, so let's make a little shopping list here. We're going to buy some coffee. We've got clothes and shoes. Let's buy a pair of shoes. We've got a Rubik's Cube. I kind of like that. Rubik's Cube. Those are fun. And let's go one more. And toilet paper. Okay, I see you guys trying to be funny here. Toilet paper. And so let's actually go on a shopping trip, a virtual and not real shopping trip, and we'll see if we can calculate the sales tax, assuming that it is at a rate of 7.5% for what we buy. So if you give me 1 second here, I should be able to share this. And so let's see if we can figure this out. Feel free to kind of type in chat as we go. Yes, it does apply online when shopping. So sales tax definitely applies online when you shop. I just don't know if it's the same. Is it the same tax rate as like Rhode Island's tax rate, or is it different than that? That's the piece I'm not sure of. Like, does it matter where you buy it? Like, you're buying online, right? So I don't know if it's your tax rate because you live in Rhode Island, or if it's the tax rate of whomever you're buying it from and where they're located, or something different. And that's what I'm not 100% sure on. But let's see if we can search up some of this stuff. Let's buy some coffee. And we'll just pick the first one here. The Mentalist ground coffee. There we go. $14.99. So we'll make a note of that. $14.99 for coffee. We want to buy a pair of shoes. And so let's type. I totally spelled coffee wrong, didn't I? That's embarrassing. Anyways, let's buy the first pair of Under Armour shoes. $49.98. So we'll make a note of that as well. $49.98. Let's buy a Rubik's Cube. A Rubik's Cube is, these ones on the left look pretty fancy, but we'll save some money and go with the $8.70 one. So $8.70. And then toilet paper will be $15.50. We'll go with this one here. $15.50. And so we'll make a note of that as well. All right. So we have all of our items now on our shopping list. We've got all of their prices. And so let's add these up and get a total for how much we're spending. And again, I'm doing this on the fly. I obviously could not look these up ahead of time, so make sure you are checking my math as I go. But we've got $14.99 plus $49.98 plus $8.70 plus $15.50, which should be $89.17. You guys getting the same thing? $89.17. Can I get some shifts? Some Jim asked. You should have entered that on the sign-in sheet, and we could have worked that in. I think it depends on where you buy, such as Walmart or Amazon. Yeah, I think that's probably how it is, wherever their headquarters are located, I'd imagine, but I don't know that for sure, so don't quote me on that. $14 for coffee. Yeah, I think it's like a big, I would imagine at least it's a big, or maybe some fancy brand, who knows. But anyways, we'll roll with the $14 coffee. Got lots of confirmations on the 89.17. Okay, that's excellent. All right, so if we want to determine the sales tax is going to equal the tax rate, which is 7.5%, but we have to use it as a decimal. So 7.5% is going to be 0.075 as a decimal times the item cost. So we spent $89.17, and so that is our cost of our items, and so we want to multiply 0.075 times 89.17, which should give us $6.69 for sales tax. And if you actually do this calculation on your calculator, you'll get 6.6877. But because we only go as far as breaking up dollars into cents, we only go to that hundredths place. We're just going to round it, and so we'll get 0.69. Hope says, I said a car, I didn't realize we were doing sales tax. Yeah, yeah, I think it would still apply for sure. And there's nothing wrong with you having submitted a car, right? I think you said like buy a Jaguar or something, and we certainly could do that. We could compute that. Let's see. If we came here and I searched, let me get this back up. We searched for let's go for a used Jaguar, see if we can find one with a price. $48,999. That is quite expensive. I think the reason I didn't pick that one is because all of the other items were like going to range between 0 and 50, and this one would throw it way out of proportion, but let's try this one as well. Let's say we wanted to compute the sales tax. I know you guys can't see my whiteboard right now, but I'll switch it back in a second. Compute sales tax on the Jaguar car, the F-Pace S, for $48,999. On the Jaguar for $48,999. And we'll use, let's go, I think somebody had said Rhode Island's tax rate. was 7%, so let's go with 7% on this one. And then let me switch back here. Okay, so we can do this one as well. I think the other thing is, I don't know about you, but I certainly cannot afford a Jaguar. So computing the sales tax, for me at least, is not terribly informative. Whereas I can at least afford to buy coffee at $14, hopefully. But let's see what we've got. Sales tax, once again, is going to equal the tax rate times the item cost. The tax rate in this case is 7%, which is 0.07 as a decimal times 48,999. And if we do that quick calculation, 0.07 times 48,999, oof, you will get $3,429.93. I'm not sure if I can even afford to pay the taxes on this car, but yeah, there we go. $3,429.93 would be just the sales tax if you bought that Jaguar we found. So there you go. Yeah, Slim Jim, we are apparently shopping for cars right now. All right, cool. Hopefully that was a little bit of fun. That is a pretty penny. That is absolutely true. That is a pretty penny. Let's see if we can come back to this example here. We've got $6.69 that we paid in tax, and we paid $89.17 for the items themselves. We might ask the question, I'll say this is part B, how much do we pay in total and there's two ways we can answer this question. We could say that, well, in total, our total cost is going to be everything that we paid for the items, so the items cost, and then plus all of the extra that we have to pay in sales tax, right? So items cost plus sales tax will give us the total cost. In other words, $89.17 plus 6.69, and if we do that math, 89.17 plus 6.69, that's going to total to $95.86. And so in total, we would be spending $95.86. 89.17 of that goes to the people who are selling the items, and the 6.69 is what's taxed and goes to the government. Now, let's notice here also the items cost 100% of what they cost, right? I mean, that's sort of a given. They cost exactly what they cost. But if we add the sales tax on top of that, plus the sales tax, which is, what we did 7.5% for this one, 7.5%. And we add those together, we've got 107.5%. Now, notice what happens here. If we took 107.5% of the item's cost, this would be 1.075 times 89.17. If you plug this into your calculator, let's see, 1.075 times 89.17, what you'll find is that this is equal to 95.86 as well. And so that's really interesting, and it's not just a coincidence that this is true. In fact, this goes way back to chapter 5 again as well, when we talked about the distributive property. Right, the distributive property, if you remember, told us that if we were multiplying some number a outside in parentheses by a sum, this would be the same as multiplying a times each of the individual numbers inside the parentheses and then adding them afterwards. So a times the quantity b plus c is the same as a times b plus a times c. And in a way, that's exactly what we have here, right? If we thought of 89.17, our item's cost, as our A in this case, then we've got 100% and 7.5%. Okay, this is like what we did in the first piece. This is what we did in part A. We found the total, then we computed the sales tax individually. Actually, I might be mixing this up. This is what we did in part... I'm losing it. Hold on. There we go. We computed the item cost first, and then added the percentages together, right, and then multiplied them afterwards to get 95.86. Or this would be the same as saying, let's take 89.17 times 100%, which is of course just 89.17, plus 89.17 times 7.5%, right, and that's exactly what we have here. 89.17 times 100% plus 89.17 times 7.5% still equals 95.86. And so either way, this actually will work the same. And that's pretty cool. Takes advantage of our distributive property. Do we have any questions on how we would calculate sales tax or total cost working with percentages? I'm lost. How so? Which piece? Basically, all I'm doing here is saying there's more than one way that we can get to this answer of 95.86. We could either first calculate the sales tax and add it on, and that's what we did first right up here. Or we could realize that we can take advantage of the distributive property and say if we're paying 100% for the item cost and paying 7.5% on the sales tax, that means in total we're paying 107.5% of whatever the items cost, and just multiply those two numbers here and still get the same 95.86. We have more than one way at which we can arrive at the solution to this problem. Once we got to part B is just calculating the total cost. Right, so when we go onto Amazon and we pick out all of these different items, right, these cost $85 or $89.17. That's not what we pay though, because we also pay $6.69 on top of that. Right? So we pay the 89 for the items cost, and then we pay the 6.69 to the government for sales tax. And if we want to find out how much we spend in total, we have to add those two up. And that's what we did in Part B. The total cost has to equal however much we paid on the items plus whatever we paid on the sales tax, and that's the actual money that leaves our pockets. All right. Now the last thing we can do today with percentages is talk about percent change. And we hear this kind of thing a lot in the world every day, right? Something increased by 10% or it dropped by 5% or things like that. And so we're going to figure out the actual specifics of that math and how even it's easy to make mistakes, and many people out there in the real world do in fact use that kind of terminology and phrasing and language incorrectly. So percent change in general, we can kind of break down into two different things. We can talk about it as either a percent increase or talk about it as a percent decrease. Percent increase, basically all this is the amount of increase, so however much we have tangibly increased by, divided by whatever the original amount was. And likewise, the percent decrease would be whatever that tangible amount that we decreased by divided by however much we started with, the original amount. And essentially when we talk about these two things, we're talking about what portion of the original amount have we increased or decreased by. And specifically when we're talking about percents, when we do what portion of a whole, we represent that out of 100 and say percent per 100. So let's look at an example. Let's say that you had a job and you were making $12 an hour. So if you were making $12 per hour at your job, and then maybe you got a raise, and then got a raise to, let's say, $15 per hour. Can we find the percent increase? Well, the percent increase is equal to the amount that we increased by, so the amount of increase, divided by the original amount. And so in this case, our original amount was 12, and we increased to 15 from 12. So to get the amount that we increased by, we can subtract the difference there. 15 minus 12 is 3, so we have gone up $3 per hour. We started at $12 per hour, so we have 3/12. Of course, we want to represent this as a percentage, so we can simplify this fraction. This is equal to 1/4, right? 3/12 is the same as a quarter. A quarter is the same as 0.25. right? And we can kind of walk through each of these steps, thinking back to what we did at the very beginning of this section, and say 3/12 is 1/4, which is 0.25, which is 25%. And so, therefore, your wages increased by 25%. And that would be our percent increase. Now, there's some times where you need to be careful with this. Let's say, for instance, if we were dealing with this same job and your boss wanted to make some cuts. And drops your wage back to $12. So dropping it from $15 per hour back to $12 per hour. $12 per hour. Can we find the percent decrease? We've got to be careful here, because you might be tempted to say, well, when we went from 12 to 15, we went up by 25, so if we're just going back, then we're going down by 25, right? That's the temptation, right? It might be tempting to say we're decreasing by 25%. But this is not true, right? Because in actuality, the percent decrease, just like percent increase, is the amount of decrease, how much we are literally dropping by, divided by the original amount. And so in this case, we are, again, changing from 15 to 12, but here we're starting at 15. Right? So our original amount in this case is 15. And so rather than having 3 over 12, like we did in the first example, here we have 3 over 15, because we've decreased by 3 from an original amount of 15. 3 out of 15, of course, we can simplify to 1 out of 5. 1 out of 5 we can rewrite as a decimal, which will be 0.20, which means 20%. So we do have to be a little bit careful on this one, but we can say that our wages decreased by 20% here. And so it's going to be important to make sure that you use these formulas for percent increase and percent decrease when you actually compute these. They are defined very specifically in this way. You can't increase by 25% from 12 to 15 and then decrease by 25% to go back to 15 to 12. I know that feels weird because it feels like you're just doing the opposite. But increasing by 25% and then decreasing by 25% would mean different things, because you're always comparing it to the starting amount. And so we get 25 and 20. Now, there is one more place where this can get really tricky, and this is where a lot of people, even in the real world, tend to mess this up a lot. So this will be where things can get tricky. And this is basically going to come down to, we've got to be extra careful. So be careful when taking percentages of percentages. Taking percentages of percents. And what I mean by this is, let's say that we were talking about something like exam scores. And let's say that maybe you scored a 75% on exam 1. And maybe you scored 85% on exam 2. We want to find the percent increase of your scores. In a case like this, it might be really tempting to say, it might be because 85 and 75 are only off by 10, that you have a 10% increase, but you're not increasing by 10%. Your score increases by 10 percentage points, but you're not making a 10% increase. And that's kind of a tricky thing to get your head around at first, because it almost sounds like you're saying the same thing, but you're not. The percent increase is always relative to the starting point. It's a multiple. It's how much are we multiplying our original value by in order to get to the new value. And this is just stating we're making a literal difference of 10 percentage points, and those two are distinct. So it's important to make that distinction. In actuality, if we were going to compute the percent increase, we would want to do the amount of increase divided by the original amount. And so the amount of increase in this case, that's your 85 minus 75. We're improving by 10 percentage points, and we want to compare that relative to the 75 points that we started with. And so our original amount is 75. Our difference is 10. The amount of increase is 10. And so 10 over 75, which is equal to 0.13 repeating, or approximately 13.3%, would be our percent increase. So although it's tempting to say, oh, we went up 10 percentage points, so we've improved by 10%, in actuality, your score has increased by 13.3%. So that's definitely something you want to be aware of whenever you are taking percentages or percent changes of percentages. Just make sure you're really careful with the language that you're using, right? In this case, we can say, yeah, I scored 10 percentage points higher, but my improvement was an improvement of 13.3%. Anyways, that's all that I have for you today. Hopefully you had some fun with the sales tax. Hopefully you're starting to feel a little bit more comfortable with percentages. I will stick around for a couple minutes if you do have questions. But otherwise, have a good rest of your day, and I will see you tomorrow or Wednesday. Have a good one, Sean. Have a good one, Kelly. Have a good one, Jaden. Bye, Hope. Have a good one, Emma.